Welcome back. Today we're going to talk about improper integrals. So this section we're going to focus on two types of improper integrals. And what is improper integral? Let's say you want to calculate the area under a function where the area is basically, let's say, from 1 to infinity. So you're looking for the function f and you want to find out the area of this section. And what you notice is that the interval that represents this integral would be from 1 to infinity of f of x dx. That means the area could be infinity, or it could be a smaller value like 2, 3, a finite number. So there are cases that we're going to discuss. One of them is that if the interval that represents the area, the boundary that we're going to focus on is going to be infinite or not. In case if the area is infinity, then we will deal with this separately. What if you have a finite interval? Let's say you have a function f. Here is f over the interval from a to b. If f is continuous over a finite length of the interval, you already know that this area is bounded. It is bounded by this specific box, so therefore it has to have a finite area. But what if the function is not bounded? Say your function looks like something like this, where b is a vertical asymptote. So the function f is increasing around b, or maybe decreasing around b. In this case, what you see is integral from a to b of f of x dx. It is possible that the integral is bounded or unbounded. In those cases, we will call it convergent or divergent, depending on if the integral has a finite value or infinite value. Similar idea could be held if the function f is, let's say, looks like this. Let's say this is the function f. Here. So let me draw it on this side, maybe it's better. Here, let's say you want to evaluate the function, the integral of a function f that looks like this. Here, from a to b. If the function involves discontinuity, that means there is a vertical asymptote somewhere. So the function is keep increasing. If you want to calculate this area under the function from a to b, you always have to break it up and say, okay, let's calculate the integral from a to c, then from c to b. You cannot just jump ahead and calculate the integral from a to b. This is the important part of this section, that if the function involves discontinuity, you have to be careful and break down the function into the sections that are connected. So like from a to c, from the interval a to c, you can calculate the integral. If it's bounded, then you find that area. Similarly, you can calculate the integral from c to b. If it's bounded, you can find the area. Then you add those two areas. That would be the resulting area from a to b. We're going to get into more details of it, but this is basically the idea for this section. And this is the improper integral. The first type that we're going to discuss is the infinite intervals. Means the interval is unbounded. You're calculating an integral from a to infinity. And instead of infinity, you can represent it with the variable t and let the variable t approach infinity. So you can calculate the integral from a to t of f of x, then take the limit of the result as t approaches to infinity. Similarly, if it's from negative infinity to b, it's an infinite interval, and you can let the negative infinity to be a variable t and calculate that integral. we say these two integrals are convergent. If this specific limit exists, then we say the result is convergent because you will get a finite number. If the result is infinity or negative infinity, then we will say the integral is divergent. That means the area is infinite. And similarly, if you're dealing from negative infinity to infinity, that means all the real number, you can break it up into two parts and say from negative infinity to some constant a, and from that constant a to infinity. You calculate each one of these two separately. A could be any number. You could pick 0, 1, 2, whatever you want to pick. So this a is just a number. Depending on how you pick the number, sometimes it becomes easier to deal with the integral. So if both of these are convergent, if this is convergent as well as this one is convergent, then the summation would be convergent, which means the integral would be convergent. Otherwise, if one of these two integrals are divergent, then the integral is divergent. Okay, so here's an example. Let's calculate this integral from 1 to infinity. So what I'm going to do is I'm going to write it in terms of a limit. You say limit t approaches to infinity. Calculate the integral from 1 to t of 1 over x dx. Ignore the limit. So the limit really doesn't matter at the moment. We just want to calculate the integral. What is the antiderivative of 1 over x? It is ln absolute value of x. Then we evaluate it over the interval from 1 to t. And this would be limit. The limit is still there, t to infinity, t to infinity. Okay, ln absolute value of t minus ln absolute value of 1. So I'm going to calculate this limit now. ln 1, this is simply 0, so I don't need to worry about that. So what is the question is, what is the limit of t approaching to infinity of ln t? And you notice that the log function, if you don't remember, here's how the log function looks like. This is ln absolute value of x, or x. As x is increasing, if the x is increasing, what happens to the y value? The y values are continuously increasing. So if x is approaching to infinity, ln x also approaches to infinity. So this means the limit ln absolute value of t would be positive infinity. And what can I say about this integral? This integral is divergent, since the limit is an unbounded value. But here, let's look at the next example. What is the integral from 1 to infinity 1 over x squared dx? Again, you can always write this limit t approaching to infinity, integral from 1 to t of 1 over x squared dx. You don't need to use t always. You can use a different variable, but since the textbook uses t, I'm going to stick with this variable. Limit t approaching to infinity. Okay, what is the antiderivative of 1 over x squared? You can write this x to the power negative 2 and integrate. It is simply negative 1 over x. This is the antiderivative of 1 over x squared. You can write it as x to the negative 2, and that is x to the negative 1 divided by negative 1, which is negative 1 over x squared. This is the antiderivative, negative 1 over x. Then we want to evaluate it from 1 to t. And this is limit t approaching to infinity, negative 1 over x, negative 1 over t minus negative 1 over 1. So now, what if we replace t with infinity? What happens? You'll get negative 1 over infinity minus negative 1 over 1. Negative 1 over infinity, or the limit of negative 1 over t, this is simply approaching 0. This is not the right way to calculate, but the limit of this term is simply 0, because the denominator is keep increasing. So this limit is 0, and you have minus 1 over 1, which is simply 1. So what can I say about this integral? It is convergent. And I found out the integral must be value of 1. That means if you draw the graph of 1 over x squared, here's how 1 over x squared looks like. This is 1 over x squared. You want to calculate the integral from 1. So 1 is somewhere here. Y value is 1 also. And you want to calculate this area. It turns out that this area is exactly 1. That integral represents this area. Okay, what if it was negative infinity? So similar idea, limit t approaching to negative infinity, integral from t to 0, x e to the x dx. So all those properties that we use for the integration, those are still hold. So in this case, for example, to calculate this integral, what do I need is I need to use the integration by part technique. So I will say, let's call u to be x, dv to be e to the x dx. I can figure out what is du equals dx, and I can integrate and figure out what is vv would be e to the x. So the limit still there. So here equals to limit t approaching to negative infinity. Okay, what is the integral? The integral would be uv. So here uv would be x e to negative x to the x, minus the integral v du, which is e to the x dx from t to 0. I will evaluate at the end, but this is supposed to be from t to 0 minus from t to 0. Okay, so let's write the next step. It would be limit x e to the x from t to 0 minus the integral of e to the x is simply e to the x from t to 0. You can evaluate at the end, or you could have done it this step, doesn't really matter. Okay, so limit, if you evaluate at 0, you'll get 0 times e to the 0 minus e to the 0, then minus, if you evaluate at t, it would be t e to the t minus e to the t, and this part, the negative, is between both as t approaches to negative infinity. Okay, so first let's calculate some of this simple. This term, 0 times that, it's 0. E to the power 0 would be 1. Okay, what is the limit t approaching to infinity of e to the t? It would be e to the negative infinity, or 1 over e to the infinity. This is also 0. How about the limit of t e to the t as t approaches to infinity? T approaching to negative infinity. If you don't remember, make sure that you look over the Hospital rule, because this, if I replace negative infinity, what do I get is I will get negative infinity times e to the negative infinity, which is basically negative infinity times 0. And we would say this is one of those cases that you require to use Hospital rule. So instead of doing this, we would say let's rewrite it in terms of limit t divided by e to the power negative t, and t approaching to negative infinity. You can move the e to the t to the denominator, make the exponent negative, and then you use the Hospital rule and say, okay, this is the same as the derivative of the numerator divided by the derivative of the denominator. Derivative of the numerator would be 1, derivative of the denominator would be negative e to negative t. This is as t approaches to negative infinity. This is from Calc 1. Make sure that you review this. Those indeterminate form of the limit were 0 over 0, infinity over infinity, and 0 times infinity. Those were the cases where we would use the Hopital rule. And so this limit now, if I replace negative infinity, what do you get in the denominator would be 1 divided by negative infinity, which is simply 0. So what I can say is this term also is 0. The limit of that becomes 0. So therefore, this results to simply negative 1. You would have minus here, minus 1. Okay, so what can I say about the integral? The integral is convergent. And we found out what is this corresponding value. Okay, just make sure that you review this Hopital rule. These were the 3 cases. Okay, what if, here's an example of what if the interval was from negative infinity to infinity. Again, you can pick any number in between as long as there is no discontinuity. If there is discontinuity in the function, then you have to deal with this, but this denominator is always positive, so there is no discontinuity in the function. And so I can write this integral as, let's say, from negative infinity to 0 of 1 over 1 plus x squared dx, plus the integral from 0 to infinity of 1 over 1 plus x squared dx. To be honest, you could do it both at the same time, but you have to create double limits. That's why they add this constant 0. Or you can write this to be 1 if you want, but 0 is a simpler case, because the antiderivative of this function would be simply arctan, and you're going to evaluate the value that you know, not something like 1 will give you pi over 4. 0 would be simply 0. So this constant that I picked, you can pick 1, 2, 3, whatever you want, but 0 would be an easier case. So let's calculate each one of these integrals separately. From negative infinity to 0, 1 over x, 1 plus x squared dx, and the integral from 0 to infinity, 1 over 1 plus x squared dx. This is the same as limit t approaching to negative infinity of the integral from t to 0, 1 over 1 plus x squared dx, and same thing down here, t approaching to positive infinity from 0 to t, 1 over 1 plus x squared dx. This integral, the top one would be limit t approaching to negative infinity of the antiderivative of that would be tan inverse of x, evaluated from t to 0, and here you would have limit t approaching to positive infinity of tan inverse of x, evaluated from t to 0. So the top one, the top limit would be tan inverse of 0 minus limit tan inverse of t, as t approaching to negative infinity. You can, I wrote this term separately without the limit because it doesn't involve t. So the limit really doesn't affect it, it's a constant. You can write the limit outside as well, it doesn't make any difference. Tan inverse of 0 is simply 0. So this would be tan inverse of negative t as t approaching to negative infinity. If you don't remember, draw the tangent. Here is the tan inverse. This is tan inverse. If t is tan inverse of t, let's say, if t is approaching to negative infinity, if you go into a negative infinity, what is the corresponding y value approaches to is negative pi half. And on the other side, you would have positive pi half. So this is negative pi half. So what you get is 0 minus pi half, which result into pi half. And exactly the same idea would be here, tan inverse. It would be limit tan inverse of t as t approaches to positive infinity minus tan inverse of 0. And this would be pi half minus 0, which is simply pi half. So this tells us that the result of this integral, the original integral, is simply pi half plus pi half, which is pi. So this is a convergent integral, and the value would be simply pi. Again, you could pick this number boundary to be 2, but then the issue would be, what is tan inverse of 2? That's why it's kind of makes sense to pick a constant that you know how to calculate the integral. It doesn't really affect anything, because if you add them together, these two tan inverses, since you're adding the result of this integral with this value, the two tan inverses will cancel out. They're opposite of each other, the tan inverses of 0. What you care about is basically the limits. Okay, so here's one more example that is kind of builds the basic for when the integral of 1 over x to the power p is convergent for what values of p. This is one of the questions that, if you know the answer to, you can simply try to figure out the convergent of other functions by comparison. We're going to discuss those in a bit, but here, let's say for what p values the integral 1 over x to the power p is convergent. If this was simply, let's say, if p was 1, what happens? You would have integral from 1 to infinity of 1 over x dx. And we already discussed this in the first example. If I go up, we discussed this and we say, okay, the result was divergent. So if p equals to 1, this was a divergent integral. What if p was not 1? So let's assume p is not 1. We break these two cases up because in cases of exponent being 1, then the integral, the result of the integral is ln. In the other cases, if you have 1 over infinity, 1 over x to some power p, then you can write this integral as x to the power, let me write the limit first. Limit 1 to t, x to the power, instead of p, I can write in the numerator as negative p dx. And now I can integrate. So what would be the integral? It would be, you add 1 to the exponent, x to the power negative p plus 1, or you can write it as 1 minus p divided by 1 minus p, or p negative p plus 1, however you prefer. Let me write it this way so there is no confusion. And you want to evaluate this from 1 to t and take a limit. Limit as t approaching to infinity. Okay, so this is simply, I'm going to rewrite it, t approaching to infinity. So you'd have 1 over 1 minus p in the denominator, and that x to the power negative p minus 1, you can write it as 1 over x to the power 1 minus p, or p minus 1. You can move it to the denominator and make the exponent opposite. Evaluate this from 1 to t. This first part, since p is not 1, this is just a constant. So I can say this is the same as 1 over 1 minus p times limit of 1 over x to the power p minus 1 as t approaches to, x to the power p minus 1 as t approaches to infinity, evaluate from 1 to t. And that is 1 over 1 minus p times limit t approaching to infinity. Let's evaluate it 1 and t. It would be 1 over t to the power p minus 1 minus 1 over 1 to the power 1 p minus 1, which is always 1. So you'll get 1. So now the question becomes, when is this value of 1 over t to the power p minus 1 is bounded? When do you have a finite value for this limit? And the answer is whenever the denominator is finite or infinity. But since t is approaching to infinity, we want infinity to be to a positive power. If you had 1 divided by infinity, this results into 0. But if you had 1 divided by infinity, let's say to the power -1, this is the same as 1 over, this is the same as infinity divided by 1. So basically, this would be infinity. So basically, what we want is this case. We want the integral, we want this fraction to be 1 divided by infinity, which means we want the exponent, the p minus 1 exponent, we want that exponent to be a positive value. Otherwise, it will move to the infinity will move to the numerator and causes the integral to be divergent. So if we want this to be finite, what you need is for this fraction to be 0. And how do you make that fraction is by letting p be greater than 1. If p is greater than 1, then this fraction is simply 0. As the limit approaches to infinity, you would have 1 divided by infinity, and this results into simply -1. And if you remember, we did an example earlier on. It was 1 divided by x squared. Here, the denominator, instead of being x to the power 1, we picked x to the power 2. 2 was greater than 1, and it resulted into the limit to be 1, and the limit was 1. Sorry, here I forgot to multiply that 1 over 1 minus p, so you'll have 1 over 1 minus p times -1, which is -1 over 1 minus p. And in case of p equal to 2, what do you get is -1 divided by 1 minus 2, which is simply +1. That's what we got in the first example, in the second example. So what we can conclude is, if p is greater than 1, then the integral of 1 over x to the power p from 1 to infinity, this is a convergent integral. This is one of the propositions that you could use when you compare other integrals with this 1 over x to the power p format. Okay, so this is enough for those examples involving infinite intervals. But what if we're dealing with discontinuous integrals? The case is when we have vertical asymptotes. Let's say you have vertical asymptote, so here at x equal to b, let's say we have vertical asymptote or discontinuity asymptote. What happens? If they ask you to calculate the integral a to b of f of x dx, since we assume a is less than b, so what are you approaching? When you're approaching b, you're approaching from left side to calculate the integral. So you can replace that boundary with the variable t, similar to the infinity, and say, let's approach b from left side. T approaches b from left side, if the vertical asymptote is at b. What if the vertical asymptote is at a? Then the interval, when you're calculating at a, you're approaching from the right hand side. So the limit, replacing a with the variable t, and you can calculate the limit as t approaches to a from the right hand side, from t approaching to a from the right hand side. And again, same idea. If these limits exist, then you would have convergent. If the limits exist, and if the limit approaches infinity or negative infinity, then we call it divergent integrals. And what if we have discontinuity in between a and b? Then you break up the integral into two parts. The part that involves the discontinuity, let's say it happens as discontinuity at a constant c in between a and b. Then you break up the integral from a to c and from c to b, and you calculate each one of these two. If one is divergent, the result would be divergent. If they're both convergent, then the integral will result in a convergent form. I wrote a couple of examples. We can go through those. So let's say they ask you to calculate this integral. What you notice is that around 2, what happens is you would have 1 divided by square root of 2 minus 2, which would be 0. So you would have 1 over 0. In terms of limit, that could be positive infinity or negative infinity depending on which direction you're approaching, but since we're approaching from right hand side, it would be positive infinity. So that means there is a vertical asymptote for the function, for this function f of x equal to 1 over square root of x minus 2. There would be a vertical asymptote at 2 because you would have 1 divided by 0. So what I'm going to do is I'm going to write this as limit from t to 5, 1 over square root of x minus 2. And what has happened to t? T approaches to 2 from right hand side. Since the interval here is 2 to 5, this continuity happens at 2, and if you pick the variable t, then t approaches to 2 from right hand side. You don't need to memorize these. You can always draw the interval and see which direction are you approaching. Okay, so how do you calculate the integral? Ignore the limit till the very end. So limit t approaches to 2 from right hand side. This integral, you can use substitution. Call x minus 2 to be the substitution. I'm going to say u equals x minus 2, then du would be dx, and you can write the integral as limit integral from t to 5. I'm not going to change the boundary because I want to replace it back later on. 1 over u du, u to the power 1/2, sorry, instead of square root of u. And this results into limit. The correct format would be to change the boundaries, to update the boundaries, but I'm going to keep it so you do not get confused in that way. The integral, we can calculate the integral. The integral would be u to the power negative 1/2, and you add 1 to the exponent, so you get u to the power 1/2 divided by 1/2. And then evaluate it from t to 5, but t to 5 is not for u, it's for x. So I'm going to replace those back in terms of x. T approaching to 2 from right hand side. You can update the boundaries instead of 5 and t, but again, since you have a limit involved, you have to be careful that you update this limit as well. So I avoid doing that. I'm going to keep the boundaries and go back and write in terms of x. U to the power 1/2 divided by 1/2 is the same as 2. U to the power 1/2, which is square root of x minus 2. And now I evaluate from t to 5. Okay, so this is limit t approaching to 2 from right hand side of 2 square root of, if you replace 5, you get 5 minus 2, minus, if you replace t, 2 square root of t minus 2. Okay, now let's evaluate. If we replace t with 2, what happens to the integral? This term, you get 2 times 0, which simply becomes 0. So this is 0. So you get 2 square root of 3. And we could calculate this integral. We ended up with a finite value. So I can say this integral is convergent. And this is convergent. And the result was 2 square root of 3. Okay. Here's another example. From 0 to pi half. Secant at 0. Secant is, if you forget, secant x is the same as 1 over cosine x. Again, always think about where these boundaries cause issue. cosine, 1 over cosine. Cosine is well defined at 0. At pi half, cosine is well defined and it's 0. So here, if I evaluate at 0 and pi half, I'm just checking to see what happens. If you evaluate at 0, secant of 0 is well defined, it's 1. If you evaluate it at pi half, secant of pi half, then this would be 1 over 0, which is undefined. This means there is a vertical asymptote at pi half. So what I'm going to do, 1 over 0. So what I'm going to do is I'm going to say, let's evaluate this integral in the form of 0 to t, limit t approaching to pi half. But if the interval is from 0 to pi half, how are we going to approach pi half? We're going to approach pi half from the left-hand side. And secant x dx. From earlier on, we know the integral of secant. If you don't remember, just look at the lecture, over the notes from the last couple of sections. We discussed that the integral of secant was ln absolute value of secant x plus tangent x. There was a trick to calculate this integral from the trigonometric section. And we want to evaluate this from 0 to t. This would be limit t approaching to pi half from left-hand side, ln of absolute value of secant t plus tangent t minus ln secant 0 plus tangent 0. Okay, let's deal with the constant. Tangent 0, simply 0. Secant 0, 1. Secant of 0, we calculate that as 1. So what you have is ln absolute value of 1. What is ln of 1? Is 0. So this term is simply 0. So what you just need to calculate at the moment is to figure out what is limit t approaching to pi half from left-hand side of ln secant of t plus tangent of t. And now let's say, what would be the limit of ln secant t? So you'll get ln secant at pi half left, secant, I'm going to write it so you guys can see it, plus tangent at pi half from left hand side. Secant at pi half from left hand side, this is positive infinity. If you don't remember how secant look like, here is this is secant x at pi half. As x approaches to pi half from left hand side, secant will increase toward positive infinity. So you would have positive infinity, and tangent at pi half would be similarly would be positive infinity. Sine pi half over cosine, yes. So this is, for tangent, would have similar structure. Tangent was like this at pi half. Tangent was increasing toward positive infinity. So what you have is ln infinity, just simply infinity. So what does it tell us? It tells us that this integral is not convergent. This is a divergent integral. Okay, just make sure that you calculate the limit correctly. Okay, how about this one? The integral 1 over x minus 2 from 0 to 3. Okay, now let's check 1 over x minus 2. If I evaluated 0, what do you get is 1 over 0 minus 2, which is 1 over negative 2, no problem. If you evaluated 3, so this is for x equal to 0, and for x equal to 3, what you get is 1 over 3 minus 2, which is equal to 1. So that means the two endpoints are not causing a discontinuity, but we might have a discontinuity somewhere in the middle. You look at the fraction and figure out where there could be discontinuity. The denominator could be 0, which causes discontinuity. So at x equal to 2, since the denominator would be 0, we would have discontinuity. So what I'm going to do is, at x equal to 2, you would get 1 over 0 for the fraction, which causes discontinuity in the function. So I'm going to rewrite this integral in terms of from 0 to 2, 1 over x minus 2 dx, and plus from 2 to 3, 1 over x minus 2 dx. And calculate each one of these two separately. So if you calculate the first integral, okay, either one of these two is fine. So let's say calculate from 2 to 3, 1 over x minus 2 dx. The integral would be limit t approaching to 2 from right hand side of the integral t to 3, 1 over x minus 2. This is the case where you have discontinuity in the middle. You always have to break it up into two sections. And what would be the result of this? Dx. And the integral would be ln absolute value of x minus 2, and then you evaluate it from t to 3. What you get is limit t approaching to 2 from right hand side, ln 3 minus 2, which is minus ln t minus 2. Okay, ln 3 minus 2, this is ln 1, which is equal to 0, so this term is 0. And then if you replace 2 from right hand side, what do you get for this ln? You'll get ln 0 from right side, ln 0 from right side, which is positive infinity. And you have a minus in between, so this results into negative infinity. That tells me that I do not need to calculate the other integral. Since this term is infinity, I can say this is divergent. Therefore, the original integral is divergent. Just make sure that you do not make mistake of forgetting that there is discontinuity, because if you forget that there is a discontinuity and ignore that discontinuity and say this is from 0 to 3, 1 over x squared, x minus 2. If you forget that discontinuity, what you get is ln absolute value of x minus 2 evaluated from 0 to 3. What you get in this case is ln 1 minus ln 2, which gives you negative ln 2. This is not the correct answer. This is not correct, this negative ln 2, since there is a discontinuity at x equals to 2. So make sure that you do not make this mistake. This is a common mistake that may happen. Okay. So this is the other type. This was the other type of the improper integral. And finally, the comparison theorem. It's very simple. This is one of the simplest theorem. It compares two functions. Let's say you have two functions f and g, and they're continuous functions. And we know some information that f is greater than g and greater than or equal to 0. So the function f is greater than g for all the x's that are greater than a. Maybe not everywhere, but for a certain area. So let's say this is the function f here. This is the function f, and we have the function g. The red one is g, the green one is f. F is not always greater than g, but after a certain point, if we call this a, then after that f is always above the function g. That means f is satisfying this condition. F is greater than g in the section from a to positive infinity. For all the x is greater than a, this is true. Then what you can say about the integral a to infinity of f? What you can say about this integral from a to infinity of f? We can say that if this green one, if this green section is bounded, which means the integral of f is convergent, then it results the fact that since g is smaller, g must be convergent as well. So if the integral of f is convergent, then since g is smaller, g must be convergent. On the other side, if this g was divergent, since g was smaller than f, then f must have been divergent as well. So if g is divergent, then f must be divergent as well. Because by comparison, since g is smaller, if g is going toward infinity, then it tells you that f must be going toward infinity as well. Okay, so make sure that you understand the concept. It's always comparing two numbers. If I say x is less than y and tell you that x is going toward infinity, there is no, you cannot say y is 3, because 3 can never be less than infinity. The only option is that y must be infinity as well. This is the divergent form. But if I tell you y is 3, then x must be less than 3. That means x cannot go toward infinity. X must be a number less than 3, like 2 or so on. So this is the comparison between f and g. Here's an example for you. Show that this function is convergent. Okay, let's keep this actually at 0. One thing that you notice is that if this starts from 0, 1, 10, 20, it doesn't really affect anything, because what you care about is not the bounded part of the function. So let's say here, if I compare this function, e to the power negative x squared, let's say it looks like somehow I don't remember exactly how it looks like. Maybe it looks like something like this. This is e to the power negative x squared. And if you compare this with a function like e to the power negative x, if you compare it with e to the power negative x, what you would notice is this e to the power negative x at 0, they both would be 1. And at the 1 they will both be. So e to the power negative x would look like something like maybe like this. This would be e to the power negative x. And then this intersection point happens at 1, because e to the power negative x squared equal e to the power negative x means that the exponent must be equal to each other. It means x squared must be equal to x, which gives you two solutions. One is 0, the other one is 1. The two intersection happens at x equal to 0 and x equal to 1. And now after that, if the exponent is decreasing larger, it means if x squared, since x squared is greater than x, for x greater than 1, for all the x is greater than 1, the more you square the exponent, the larger they become. Then since you multiply a negative to it, you will get negative x squared would be less than negative x. And this implies that e to the power negative x squared is less than e to the power negative x by raising both sides to the power e. So what you can say is this function f is always less than the function g. How can I show that this integral is convergent? I can say, let's focus on the section. By the way, this is true for x greater than 1, not for x greater than 0. But from 0 to 1, this is a finite area. It doesn't affect anything. If you add 2 or 3, if you add a finite value, it doesn't really affect anything. So I'm going to calculate the integral from 1 to infinity of e to the negative x dx. And let's say this would become from 1 to t limit t approaching to infinity, 1 to t e to the power negative x dx, and that is limit e to the power negative x from negative e to the power negative x from 1 to t approaching to infinity. If you replace infinity, the result of the limit would be 0. If you replace 1, you will get e to the power 1. E to the power negative 1, sorry. So what do you have is 1 over e. So what does it tell me? It tells me that this integral is finite, and the integral is 1 over e. That means this red section is bounded. What does it tell me about the area under the graph of e squared? Since it's supposed to be smaller than the red one, I can say this integral from 1 to infinity of e to the power negative x squared dx is supposed to be less than or equal to the integral from 1 to infinity of e to the power negative x dx. Which means, since this integral we calculated it and it was a finite value 1 over e, then the integral of 1 to infinity of e to the power negative x squared dx must be less than that constant. So which tells me that the integral must be convergent. Okay, so this is how you compare it. Compare it over the section. So if this integral is convergent, since you can write this as 0 to 1 integral plus 1 to infinity, this part is convergent. This is a bounded area. So this is finite number. Any finite number plus another finite number, it's going to give you a finite value. So that means the integral must be convergent. This is how you compare two integrals and resulting into convergence. You don't need to figure out the value. The value is not that easy to calculate for this integral, but later on, hopefully in Calc 3, we will figure out the value of this integral as well. Or maybe later on, actually, in this textbook. I'm not sure about that, but it's not that easy to calculate. Okay, how about this one? Show that this is divergent by comparison. Here's one thing that we learned was if we had the integral from 1 to infinity of 1 over x dx. This is the first example that I started with. We learned that this was divergent integral. Just because the x to the power p, if p was 1, then we had divergence. Normally, if you're dealing with x in the denominator, this is the structure. You compare it with such an integral. And if you look at the numerator, 1 plus e to the power negative x is always greater than 1. That means if I divide both sides by x, this is still greater than 1 over x. So if I'm comparing the two integrals, if I'm comparing integral from 1 to infinity of 1 over x, this is less than the integral of 1 to infinity of 1 plus e to the power negative x over x dx dx. Not equal, less than. What do I know about this integral? As I mentioned, this integral was divergent, so which means approaches to infinity, this becomes infinity. You have an integral that is greater than infinity. The only way that this integral could be greater than infinity is if this one is infinity as well, which implies that this integral is divergent. Okay, it's very basic. You just need to figure out how do you compare it to what kind of function you can compare it with. And normally you pick the ones that are the simplest. It's most of the time it's x1 over x to the power p is the comparison. X to the power 1 is the common one, 1 to infinity. This is the common comparison integral. Okay, so this is enough for this section. I'm going to stop here and we will catch up with the next section in next class. Let me stop this.